What if the biggest challenge facing quantum computers isn't making them more powerful, but simply preventing them from forgetting their quantum information? This challenge is known as decoherence, and it is one of the most important concepts in quantum computing. To understand decoherence, we first need to understand what makes a quantum computer different from a classical computer. A normal computer uses bits. Each bit can only be a 0 or a 1. Every app, website, and video game ultimately runs on billions of these bits. Quantum computers use qubits, or quantum bits. Unlike ordinary bits, qubits can exist in a state called superposition. Instead of being only 0 or only 1, they can exist in a combination of both states at the same time. Quantum computers can also use entanglement, a phenomenon where multiple qubits become linked together in ways that classical physics cannot explain. These unique properties give quantum computers the potential to solve certain problems much faster than classical machines. But there is a problem. Quantum states are extremely fragile. A qubit is constantly surrounded by its environment. Heat, vibrations, electromagnetic waves, and even tiny interactions with nearby particles can disturb its quantum state. When these interactions occur, decoherence begins. Decoherence is the process by which a quantum system loses its quantum properties because information leaks into the environment. As this happens, superposition starts to disappear and entanglement breaks down. The qubit gradually stops behaving like a quantum object and begins acting more like a classical bit. Imagine trying to keep a perfectly still ripple pattern on a pond. The moment wind, rain, or falling leaves disturb the water, the pattern is destroyed. Decoherence works in a similar way. The environment continuously disrupts the delicate quantum states that quantum computers depend on. This is a major problem because quantum algorithms require coherence, meaning qubits must maintain their quantum behavior long enough to complete a calculation. If decoherence happens too quickly, errors appear and the computation may fail. In fact, decoherence is one of the main reasons why building large-scale quantum computers is so difficult. Scientists spend enormous effort trying to reduce its effects. Many quantum processors operate at temperatures close to absolute zero, making them colder than most places in the universe. These extremely low temperatures reduce unwanted interactions that can disturb qubits. Researchers also use shielding systems to block external noise and develop advanced techniques called quantum error correction. These methods help detect and fix errors caused by decoherence before they ruin a calculation. But decoherence is important for more than just quantum computers. It may also explain why the world around us appears classical. Quantum mechanics predicts that particles can exist in superpositions, yet we never observe everyday objects existing in multiple states at once. One leading explanation is that large objects interact with their environments so strongly that decoherence happens almost instantly. Their quantum behavior becomes hidden, making the world appear classical and predictable. This makes decoherence one of the most fascinating ideas in physics. It connects the strange quantum world with the ordinary world we experience every day. For quantum engineers, decoherence is the obstacle standing in the way of powerful quantum computers. For physicists, it may be one of the keys to understanding how reality itself emerges from the laws of quantum mechanics. And until scientists learn to control it more effectively, the future of quantum computing will continue to depend on winning the battle against decoherence.